It was very strange. So there was just no video there for me to upload. I was like, well, shit. And Joseph, you need your quiz back. Anybody else stumble in? Did you get your quiz back? What is all this? Oh, these are correction. Wait. Did you get your quiz back, Joseph? No. Okay. Oh, Jeff is going insane in front of your eyes. Let's see. This is all stuff he turned in. Oh, Jeff. I'm hiding stuff from myself. That's always good. Oh, you got some? Oh, shit. All right. I have so little time, and here I am just not using it very well. But okay, so last time, if I remember correctly, I did talk about Cramer's rule. Is that true? I'm pretty sure I did. I know it seemed very brief, but there's really not that much to it, to be honest. It's something we do sometimes teach, or let me say it this way. We used to teach it in pre-calculus, and it's basically gone away. We used to do a lot more in pre-calculus with matrices, and it's just sort of over the years, it's kind of gone away. By the way, this is how I'm living now. I'm true ultra nerd. Look at that. Okay. Last time we talked about, is everybody cool with the idea of how to just do a basic determinant? Does anyone feel like the process eludes you? Like a 2 by 2, we've known how to do those for a while. Without even knowing that's what we're doing. That's that AD minus BC that we use for getting the inverse. That kind of was evidence that if the determinant is 0, things are not going to work as well as we might hope, right? Now we've done enough with the determinant that I can ask you, if the determinant is 0, what does that seem would mean is true about the matrix itself? Why would it not be invertible? What's more fundamentally true about the matrix? If you row reduce it, it would have a 0 somewhere in the pivot, right? You guys with me? And that sort of came out of some of the more basic properties of determinants. If I have two dependent columns, or if I have a row of zeros, if the determinant is 0, yes? And then that 2 by 2 inverse process kind of like reinforces this idea that if the determinant is 0, things are bad. So the determinant seems to be somehow related to an overall measure of the diagonal of the matrix, if I diagonalize the matrix, yes? Okay. And that kind of becomes a side note. Oh yeah, if it's 0, then you can't, I guess you can't find the inverse. Okay. So everybody feels okay? Like if I ask you to find the determinant of this, that would be totally cool? Okay, we'll do it then. Okay. Okay. So last time, very quickly, we talked about, there's one little thing we kind of danced around, and to be honest, I'm going to continue to dance around it a little bit out of an interest of time. But if I have a matrix A, in fact, let's do this. I'm going to make a 2 by 2 matrix with your help. Can somebody give me decent numbers that aren't crazy?
3, 7.
Do it again.
3, 7.
3, 7. Now somebody else give me 2 more.
1 and 9.
1 and 9. Kick ass. Or is that an invertible matrix? You can tell very quickly because the columns are obviously not dependent, but if you do AD minus BC, yeah. So for a 2 by 2, you don't really have to check. You can just see it, right? Does that make sense? For a 2 by 2, there's only 2 column vectors, so they have to be multiples of each other to have a problem. Is that cool? Okay. So, what is the determinant of this matrix, though? Let me write it like, Yeah, 27 minus 7, so 20. All right, somebody else give me two numbers. Maybe one of them negative, not too bad. Negative 2, 5? Okay, somebody else, go for it. You suck. I think I heard you say 1, 2. Is that what you said? Yes, okay. All right, so so very quickly, that's obviously invertible, but just, what's its determinant? What's the determinant of B? Yeah, negative 4 plus 5, well, negative 4, oh, not negative 4 minus 5, negative 9, yeah, okay. Now, can you guys take a moment and just figure out what AB is? Take a moment. Maybe I'll just do this with you. Oh, yeah, 23. Okay, Jeff, there you go. So this is matrix AB. What is the determinant of AB? So let's see this. 23 minus 7 times 9, 7 times 30, 7 times 29, 7 times 30 is 210. 1 less 7 is 203. Is that cool? So it'll be minus 203, which is negative 180. No, 6. Now, real quick. If I take the determinant of A times the determinant of B, I get the determinant of AB. Yes, 20 times negative 9. Okay. So, you could prove this by using elementary matrices. Do you remember those? Any matrix, I can kind of like base it off of the identity matrix through elementary matrices. So an elementary matrix could be triple this row, add this row to this row. So they kind of, each elementary matrix has like one operation it wants you to do. And they're all one step away from the identity. And based on the groundwork of how determinants work that we went through, that list that I developed before we even kind of worked with determinants, do you guys remember this? If I'm one step away from the identity, I have an easy ass determinant to do, yes? Okay, so again, in the interest of time, you could prove this fact, but it's kind of evident based on how determinants are defined that they should work this way. Okay. So another thing, before I get too far, Cramer's rule. Basically what Cramer's rule says, I'm not going to run through the whole thing again. If I have a matrix A times x equaling a vector B, if I take the matrix A, take the determinant of A times, let me see if I can say this correctly to you guys. There's no way around it, Jeff. You're just going to have to write it. Okay, A1, A2, A3, X1, X2, X3, B1, B2, B3. If I take, so here's one example. If I replace one of these rows with this vector, which seems incredibly weird. Sorry, no, the other way around. Let me do this. If I do this, and I blow this up to be like this, and I also blow up the B vector to be, not blow it up because I want to, but because I have to. A1 dotted with this is the B's. A2 dotted with this would be A2, yes? And A3, this will be A3. So if I just
So what I get here is this matrix replacing the first one with B, with the B vector. Then I'll get the determinant of this times the determinant of this, which is x1, and you'll notice this little minor is the only way I get a determinant of not 0 for one of these little minors if I blow it up around this column, equals the determinant of something I'll call B1, which is just the A matrix replacing B in the first place. Then I'll have a way to solve for x1. So here's the main idea. If I'm given ax equals b, I take b and I shove it into the first column vector of A, and then I take the determinant of A and the determinant of that new matrix, and then divide them and I get x1. If I shove b into the second column of A and do all that, I'll get the answer for x2. That is weird. And when we show it to, like, when we used to show it to pre-calculus students, we weren't able to explain why it worked. But, I mean, you can follow what we did here, and you can see why it works. So, let me see, does it have an example? Sort of. Nah. Yeah, this is quick. Here, let's do a concrete example. Okay, very quick. Okay, so 2x1 plus x2 equals 1. x1 plus x2 plus x3 equals 0. x2 plus 2x3 equals 0. So A is this matrix. Okay, that's a nice matrix. What's really nice about that matrix?
There's zeros.
Zeros are always nice to see zeros, right? Zeros are our friends.
It's also symmetric.
It's also symmetric, which is nifty. Doesn't have to be, but it just is. And my B vector is 1, 0, 0. So what is the determinant of A? Take a minute and figure out. By the way, do you guys remember? So, if I ever have a row or a column that has a 0 in it, I take the one that has the most zeros. So in this case, it's either the first row or the first column, correct? And I blow my determinant process up around it. Does that make sense what I just said? You told me earlier you were cool with finding determinants. So everything I just said is based on how to find this guy's determinant. So you're like, oh, I was lying earlier, John. All right. So the way to do this is, if I pick, you guys tell me, first thing you hear, first row or first column, which one? Column, okay, that's the first thing I heard well enough to know what the hell they're saying. So if I blow it up around this, it'll be 2 times the determinant of what? 2, 1, 1, 2, yes? That little offset, the one that you get if you remove everything that 2 is in? 2, 1, 1, 2. Jeff, that's awesome. What do you have to be careful about when you put this one down? Minus, good. 1 times 1, 0, 1, 2. And then, of course, who cares? I love it. So then you get 2 times 3, yes? Minus 1 times 2, is that cool? Okay. You guys with me? Compared to some of the stuff we've done, determinant is awesome. It's very concrete. Okay. Now, if I rewrite A, but I throw B into the first place, what's the determinant of this matrix? And now you see why I've chosen B as I did. Obviously, you're going to use what to blow it up? First column, it's got 2 zeros. You can't beat that shit. You only have one little mini determinant to calculate that. Yes? And now you start to see why upper triangular stuff and all that kind of stuff is beautiful for determinants. It's just the product of the diagonals. Now, why is this not the product of the diagonals? Because this has got a 1 here, yes? If there was a 0 here, if I blew it up around here, this would be 4 minus 0. So it would just be the product of the diagonal numbers, correct? So if I have a lower or upper triangular matrix, the determinant's stupid easy to find. You just multiply the things along the diagonal. Yes? Maybe? Screw you, Jeff? Okay. So what do you... By the way, this is, yeah. So what do you get? Sorry? Yeah, you get 4 minus 1, you get 3, yes? Is that right? Okay, okay. And then if I take and I divide, to get x1, I just have to divide the determinant of b1 by the determinant of a, which is 3 divided by 4. So x1 is 3/4. And then I could do it again with x2, x3. You guys got it with me? Can you imagine, I mean, real quick, finding a determinant versus Gaussian elimination? Yes? Which one would you rather do? Determinant. Even if there were no zeros in the damn thing, I'd rather do a determinant. Which one do you think is easier to program or takes less time to run as the subroutine or something? I mean, determinants, the computers just eat those up. Yes? So this is actually pretty powerful. No matter how big of a matrix, I just have to take B and put it in each column one at a time. Now I'll get x1 in the first, x2 in the second. It's kind of silly. That is just an example of an application of determinants. I just can't win with my classes, man.
Put in the second one, you keep the old one as A1? First column?
Yeah, you only change one at a time, so you start over. So I just chose to replace the first one. Now you kind of start over, and now you just replace the second column with B, 1, 0, 0, yeah.
Okay.
And then you'll get the answer for x2. So we're solving the system of equations in a way that I think you agree with me is most of the time going to be quicker than a full Gaussian elimination. Now, in specific cases, with Gaussian elimination, maybe be quicker. Yeah, depends on how much work there is to do for it. Okay, maybe. And again, you can look at this as just an interesting little side note. It's an application of determinants. Oh, and one little thing I used in this. Oh yeah, we already talked about that. That's true. So just remember that the determinant of AB is the determinant of A times the determinant of B. And you can extend that to A, B, C, and so forth. It's kind of crazy. Okay. Now there's a kind of a funky, I can't remember how Strang illustrates this, but there's, very quickly, if I, what was the thing we just were using? You're amazing, Jeff. Let me see. Oh, here it is. 2, 1, 0. 1, 2, 1, 0, 1, 2. Based on what we just did, is this invertible? Yes, okay. So, here's a very funky little... It's called the adjoint of A, which kind of sounds like something your dentist might say you have trouble with. Looks like your adjoint is irritated. It could just be me. So the adjoint is a weird little dude. I'm not gonna spend a ton of time on this, but it's basically, can somebody help me out? What is the Yeah. I want to make sure that I am thinking right. Am I thinking right? I think I am thinking right, maybe. C13, yeah, C13 would be, wait. Sorry, I want to make sure I'm not thinking about this backwards. Oh yeah, there we go. No. All right, let's see if I remember this. Rah. The adjoint is the matrix of values you get from the various minors in your matrix. So, for example, this is a minor here, yes? This is a minor here, this is a minor here. These two are kind of collectively make a minor of the matrix, yes? Oh, shoot, hold on. There's one piece of it that I think I've got backwards in my head. I want to double check. This is a very strange little side note. Did I bring that little bit? Oh, maybe it's here. Yeah, here we go. Beautiful. Yeah. Okay. Yeah, there we go. Perfect. Okay, I'm being silly. So real quick, that's what I was thinking about. I was thinking. Okay. Let me explain this to you, and then I'll tell you what I was having trouble remembering. So if I want to make the adjoint of A, it's going to take a little bit of work. This first element is going to be if I was using 2 to start building a determinant, wouldn't 2, 1, 1, 2 down here be the minor? And what would its determinant be? Yeah, 4 minus 1, so I'm going to put a 3 there. Do you see the idea? So if I move to the next space, so I'm going to end up with a 3 by 3 matrix. My adjoint is a 3 by 3 matrix. I really don't want to spend a ton of time on this. So if I move to this one, what would the minor be? 1, 1, 0, 2, yes? Oh, I see what you're doing.
Yeah.
Okay, my fault. Then you get 2, yes? Are you guys seeing how this kind of gets put together? So if I look at this spot, then I'm going to pretend like, what's this guy's minor? It would be this matrix, 1, 1, 0, 2, yes? And it's got a determinant of 2. Okay. And if you keep going like that, you find out that this is very silly, by the way, the inverse is equal to 1 over the determinant of A times this adjoint of A. All right, that's all the time I want to spend talking about that because it's a weird little thing. So the adjoint of A is a matrix, but that matrix is made up of values, of determinants, of minors. Okay.
This is the only way to find the inverse.
It's not the only way, definitely not. We know how to get the inverse. That's why I don't want to spend so much time on this, because this is, unless you're going to have to do that for other purposes, there's no reason to only do that because you want the inverse. Does that make sense? So this is kind of a little side note that I'm not going to spend a ton of time on. Yes, okay, here come the big ones. Something we're finally talking about that I can't believe we haven't talked about before now. Cross products.
Is this 5-2?
Yeah. I'm kind of doing all of chapter 5 at once, by the way. So if you're in my 281, we definitely talked about cross products quite a while ago. In this class, we talked about inner products. We talked about outer products, which we didn't talk about in 281. So don't feel all that special 281. But cross products, you've been living by that. And I don't think we've talked about it besides kind of indirectly in here. Correct me if I'm wrong. But if I'm given 2 vectors, the cross product, the result of the cross product is a vector that is orthogonal to both. The weird thing about the cross product is it only directly works in R3. There are operations that are like extensions to the cross products for other dimensions. Why wouldn't it work in R2, for example? Because if I take 2 vectors in R2 and I cross them, it doesn't have another dimension to go pop into to be orthogonal. Are you guys with me? The only way to be orthogonal to 2 vectors is to somehow pop out of the plane they're in. And if you're in R2, that's all you got, buddy. You with me? Is that okay? Okay. So if I'm given 2 vectors, let's say I'm given the vectors, doesn't matter, Jeff. I'm going to do it like string. 1, 2, 3. And -1, 3, 4. Sure, I like it. That's awesome. The shortcut to do this. What happened over there? Oh, it's weird. Sorry. All right, very quickly. From my perspective, the student who just left. Oh, there's Joe. Okay, I thought he opened the door with his mind, and then he got up and walked through it. And I was like, that's a neat way to find out somebody's got powers. Okay. Sorry. I had to share that because it was really tripping me up. If you're in my 281, be quiet. So if I want to figure this out, and I can't remember if this has come up in here or not, so excuse me, but one way to represent this vector is like this. Yeah, I know I've talked about I, J, and K. That's the 1, 0, 0, 0, 1, 0, 0, 0, 1 beautiful building blocks, yes? Okay. So this will be -1i plus 3j plus 4k. So if I want to find the cross product of these two things, and the really neat thing is, I love this shit because you'll do all this math and it doesn't seem, and then you end up with this vector that is magically orthogonal to both. Now in 281, we got a little bit deeper into why this process ends up with a vector that's orthogonal to both. But in here, if I set up this determinant, now this is very different. This is, we've never seen a determinant or a matrix with I, J, and K in it, or anything that wasn't letters representing numbers or numbers themselves. This kind of thing happens a decent amount. Sometimes the determinant is just a nice way to collect a lot of work you have to do. So if I do the determinant, I'm actually doing the math that's required of me. So who am I 281? So real quick, if I normally, of course, you're going to do it around this row because otherwise it gets kind of weird. But there's a shortcut to this. So I mean, if I wanted to, I could do. I'm going to kind of start it. So this would be I times 2, 3, 3, 4. Is that cool? Minus j times 1, 3, -1, 4. Plus k times 1, 2, -1, 3. Now, I want you to realize something. I showed you guys in 281 the shortcut for this, but does this involve a lot of work? No, so here, all right. I will show you the shortcut just in case, but it's not that much of a shortcut. So what do you get here? -1, so -I.
Plus 7.
Yeah, 7, so this would be minus 7j.
And 5.
Yeah, did I write that down right? Yes. 5k. So then the vector -1, -7, 5. Can you very quickly tell, is it orthogonal to this? 1 minus 21 plus 20.
Yeah.
And then -1 minus 14 is -15 plus 15. So, that's cool. That's just nifty. Yes? Okay. It also happens that if I wanted to know the area of the parallelogram, defined by U and V. So what I mean by that is U, V. They define this parallelogram, yes? All I need is those two vectors and I see the parallelogram. To get this area, it would just be the length of the cross product of the vectors. Now, there's a 281, we really focus on the connection between cross product in terms of determinant and the cross product in terms of sine and cosine and so forth. So there's like the dot product. In this class, we talked about how the dot product is related to the cosine. Yes? That's how you can find the angle between two vectors. You guys with me? The inverse cosine of the dot and over the length, blah, blah, blah. the cross product length of the cross product is actually equal to the length of u, the length of v, times the sine of the angle between them. And unbelievably fast. All I need to get for the area of this parallelogram is its height, and then I can multiply the height times the base. Well, the height would be, this is the hypotenuse. So if I look at the length of u times sine theta, and then I multiply that by the length of v, well, that's what I freaking get. Okay, that was really, really fast. I don't care. Again, these are all sort of side notes as to what determinants can do for us. So what is true if u and v are parallel? What's u cross v? Yeah, it'll be 0. And think about it, real quick, if u and v are parallel, the vectors that define their direction have to be how related? If u and v are parallel, the vectors that define the direction they're going in must be how related? Multiples. If you build the determinant, ijk vector, what's your vector? So, what's going to happen if you row reduce that? You're going to row zeros. Now, you don't have to row reduce it. If you do row reduce, you get zeros, you know the determinant from the beginning will be 0. You guys know? And also, of course, look at the sine theta. If they're parallel, theta 0. Sine 0 is 0. Yes? Maybe? Okay. So I love the cross and dot product when you really get deep into it. You can see the beautiful connection between the trig stuff and the geometry of what they're supposed to represent. Okay. And more fundamentally, I can't stop talking about this stupid thing. Hold on. If I have two vectors and I want to know what's orthogonal to both, it's got to be something pointing out of the plane. That's the only way I could be orthogonal to both of these vectors. I can have a vector in the plane that is orthogonal to both of these vectors. If I have two vectors that are parallel, how many vectors are perpendicular to this line? Infinite number of vectors. So the answer comes out to be 0 because it's like it doesn't exist because there's an infinite number of things it could be. So that's another kind of way to see why the answer makes sense. Okay. Oh. Oh, cool. Last little thing I think about applications of determinants. Well, maybe two more things. Sorry. Yeah. How many of you guys took differential equations? Anybody? And again, it's not a prereq, but anybody take it? Yes, a few of you guys. There's an idea called the Wronskian. Yes? It leaves a little something. You guys paid attention? All right. Sorry. So the Wronskian is really, really, really funky. Do you remember how you can have a vector space composed of functions? We talked about that for a little bit before, a couple times very quickly. Like a basis set would be sort of 1x squared. That's the basis set for creating all the quadratics. Yes? So the Wronskian is a nifty way, and again, I'm not going to try to prove this right now, but
This is 5-3.
this is still 5. I don't even know, dude. I'm doing all of 5 right now.
No,
Yeah. I think I'm in 5-3 now. Who knows? 5-3? Okay. So if I'm given, for example, 3 functions, let's say 3, g of x, let's say, is 4x, and h of x is 5x minus 7. Let's do this. All right. Everybody ramp this up a little bit. Let's make this 3x, 4x squared, 5x squared minus 7. Okay. You guys all with me? 3x, 4x squared, 5x squared minus 7. If I construct a determinant where I put F, G, H, F prime, G prime, H prime, F double prime, G double prime, H double prime. So you can tell if I have 4 functions, I would go down to, I want to make this square, yes? Okay. I would go down to 4 rows, I go down to the 3rd derivative. So if I want to create this thing, it would be 3x, 4x squared, 5x squared minus 7, 3, 8x, 10x, 0, 8, 10. Yes? Oh, I can almost see.
Blah, 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 blah.
Good. All right, I like it. So this determinant, which do you have a row or a column you want to build this determinant around?
First column.
Hell yeah. King of not enough room strikes again here. Let's see. So 3x times this determinant. This would be 80x minus 80x. Is that cool? Do you guys see that? Minus 3 times, let me write this down, this determinant. So what do I get here?
40x squared
Yeah, minus, wait, sorry. Why am I doing that? 40x squared minus 40x squared plus 56. I lost somebody somewhere. Damn it. It's alright, John. Doing this a little fast. Let me see. There. There. And then that would be 0.
Wait, was it minus 3? Would it be 4?
Where are we at? Sorry?
Oh, never mind.
Yeah, 3x minus 3 times this determinant.
Yeah, I got so now.
If, well, okay. I'm not sure what I did there. It's too bad, Jeff. Ah, that's not good. Oh, yeah, okay. Wait a minute. Let me see. I'm not going to spend all the time. Do you agree that these... Oh, I see what I did. Oh my God. Okay, I'm fine. Continuing. If I just had a little bit of faith. This would be negative 3 times 56, yes? So it'd be negative 168, is that cool?
Yeah.
Okay. Ooh, I did that in my head. Did I? Okay. What I did, I forgot. I threw another X in there. Can you guys look at the original and tell me? Originally, what I had was dependent.
Yeah.
Because this was a constant, this was a constant, and these were both based on X. Now these 3 are... Do you see how these 3 are independent? This guy has the X market. This guy has the X squared market. This guy has the number market. Do you see how they each have a direction that the other ones are missing? So what I was expecting was to get a 0, because the way I first put it together, they were supposed to be dependent. Are you with me? So if I would have made that a minus 7x, then it would have come out to 0, because then they would have been dependent. So if you set up the Wronskian, it identifies if your functions you're working with are linearly independent. In differential equations, that's important, because you want to write your answer to a differential equation as a combination of functions, and you don't want to have a function in there that's already represented by some other combination. So you want to make sure that they're actually independent. Okay. So again, just another application of determinants that's not just pure numbers. All right. That's Jeff setting himself up. Okay. Let me see, was there any other things I wanted to say about determinants before I move on? I am going to try to So tonight I'm gonna put together a practice test for you guys. I also kind of want to start to write up, sort of like I did once before, at least I think, kind of like a notes page for the last few things we've done. Just because I think that would be kind of helpful, especially for chapter 5, because I did kind of go through that pretty quickly. The main thing with 5 is, can you get a determinant? And then you've got all these little separate applications of determinants, yes? Okay, so it's all based on, are you able to take the determinant of this given matrix? Okay. So, what I want to get into now is a really, 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 really nifty idea. And I wish I had had enough time. I'm going to try to do something right now, which is always exciting. I don't want that. Oh, where'd I put you? I'm so evil to myself. Let me ask you this. Let me see. Oh, hold on. There it is. See if I have an example I can do. Yes, okay, beautiful. All right, beautiful, okay. So watch this. If I take this matrix, by the way, we are now in chapter 6. Holy shit, Jeff. What the shit. Okay. 5 has got 3 sections. We'll see if you agree with me. They're not that heavy. But Strang, you know, Strang has a way of making problems heavy. If I take this matrix, and let's try to multiply that by, see if I can keep this straight. Yeah. This vector. Go ahead and multiply that together. Oh. See if I can get a more interesting example. Yeah, it's not interesting. Oh, that's right. I could have. I totally could have. Dang it. Damn you, Jeff. All right, what are you guys getting? I'm sorry. 510. Can anyone see a connection between the matrix, I'm not sorry, the vector and the answer? Yeah. This is the beginning of a journey into an idea about certain matrices along with certain vectors. Together end up acting as if the entire matrix was just a single multiple. What's another way to get the same answer starting with 1, 2? Start with 1, 2. What do I do to it to get this? There's no fraction, Jeff. Multiply by 5. So somehow this whole matrix, when coupled with this vector, acts like it's multiplying by 5.